from the last video, we ended up with this equation, and we noticed that this equation has 48 different intercepts. Okay, and it has one slope. So this slope is common for all entities, but every entity has a regression line with a different slope. Okay, so how could we estimate this? We can estimate it by two methods. We can estimate it by using dummy variables, one for each entity, or we can use it by a method which is called entity demeaned or within transformation. Let's start with the dummy variable, because this is actually the easiest to comprehend. So what you have here is that you create dummy variables, one dummy variable per state, and this dummy variable is 1 if the state is correct and 0 otherwise. So then you would have the entity, and you would have the year, and you would have the y and the x, and then you would create dummy variables, one for each state. Okay, and dummy variable for state 2, and so on. Okay, 48 different dummy variables. And then you can actually write the equation as fatality rate equals a common intercept and plus the beer tax and these adjustments for the intercept depending on the state. Okay, so here you would have 47 different dummy variables, one less than the number of entities, so we don't fall into the dummy variable trap, and our base case is the first state. So this procedure is quite simple. You can just expand the data set and perform the regression, and this is called the least squares dummy variable method. So because of the dummy variable trap, we only contain or include 47 different dummy variables in our model. And when you choose which dummy to include, it really doesn't matter. So you can exclude any dummy variable, and that would be the base case, and the other coefficients on the dummy variables would just tell you the difference between the base case and the one left out, which is the base case, and the corresponding dummy variable. So, and this OLS, it's minimizing the sum of squared residuals, and here we have the actual fatality rate per over time and entity. So this would be over states, and this would be the sum over years. Okay, and if you have this double summation, you can just put 1 into the I and t, and then you calculate this squared residual, and then you just up the n, or the t, I mean, by 1 to look at the next year, but the same entity, and you calculate the actual fatality rate minus the fitted fatality rate, and then you just continue to calculate the fitted minus, or the actual minus the fitted fatality rate squared, and sum all these numbers together. And you the OLS chooses the intercept, the slope, and the coefficients on the dummy variables, so as to minimize this sum of squared residuals. And one question is, what's the relationship between equation 3, which is here, and equation 2 here? So here we have n intercepts, right? Whereas here we have 1 intercept, and we have n minus 1 different coefficients on the dummy variables. What you would see is that this alpha I is actually equal to beta naught plus the different gammas. Okay, so the intercept in equation 2 is just the sum of the intercept in equation 3 plus the adjustment from the base case. And the intercept for the base case in equation 3 is just the beta naught. Okay? So here, these two models, they are actually telling you exactly the same. They are giving you the same information. So this is a simple way to to estimate equation 2 by using the information in equation 3. So the other method is the entity demeaned or within transformation. This is a bit more tricky one, but here it goes. Okay, so we have 48 different states in our data, but in many applications, the number of entities can be very large, and the number of times in our timestamps in our data can also be very large. So when n is very large, then we have a lot of dummy variables, and it takes time to calculate these variables. And if we do not need the information on these intercepts, then we can use this method, because this entity demeaned or within transformation will only give you the correct beta. So this gives us beta, but not the alpha I, okay, or the beta naught hat and gamma I, okay, equivalently. So most software actually use this method because it's so much faster. What is it? Well, we have 2 steps. In the first step, we just subtract the mean of the variable, the y variable, and Then we use the ordinary least squares, the regression method, on the demeaned data. So the first step is a bit tricky to get the hang of. Okay. So we have this equation 2. Equation 2, we have it here, with the fatality rate equal to the entity-dependent intercept plus beta 1 times Beer tax plus the residual. Okay. What we can do is that we can create a demeaned fatality rate for each entity. Okay, for each entity. So what does it do? Well, you have, in our data set, we have 7 different timestamps. Okay, so for each entity, for each state, we take the average of the fatality rate in these timestamps, okay, in these 7 years. So here we would have, for example, fatality rate for Alabama would be equal to 1/7 times the sum, and the sum is just numbers added together, right? Would be the fatality rate for 1982 plus fatality rate in 1983, and so on, until fatality rate in 1988, right? Okay, so this would be the average fatality rate over those years, and you create one of these for, this is Alabama, just A for short, and you create 48 of these demeaned, or these means from the data set. Okay, and then you have the fatality rate, the average fatality rate equals beta times the average Beer tax over those years plus the alpha I plus the ui. Alpha I is a constant, so its mean is just the constant itself. Okay, so how can we use this? We can use this by subtracting equation 5 from equation 2. Okay, so what we do is this: we can subtract equation 5 from equation 2, and what are we left with? We are left with the fatality rate, the actual fatality rate for these 7 years, minus the mean of the fatality rate over the 7 years, and we do that for every single entity. Okay, and when we subtract these two equations from each other, we see that this alpha term, this constant, which varies across entities, it falls away. Okay, so what you're left with is this regression without the intercept. Okay, so no intercept. Okay, and in the next step, you can just use the ordinary least squares to estimate this transformed data right? This new equation without intercept, and you only have one coefficient, okay? So you're left with only one coefficient. So, and why is that okay? Well, by demeaning the variables in equation 6, the alpha terms, they dropped out, and we only had one coefficient left. And what was our question from the beginning? It was the causal effect of the x variable on the y variable. We did not care about the intercepts, but we wanted to control for any fixed effects among the entities. Okay. So we are left with the causal effect of beta 1, or the estimated causal effect of beta 1, which was our point from the beginning.